This is the last of our videos for stoichiometry, studying that heart of chemistry, the mole, and the variety of ways we move in and out of that heart of chemistry. And we're going to be doing another AP question to prepare you for some of the homework you'll be doing on your AP questions. So let's dive right in. Now, in this case, we are going to be doing an empirical formula from combustion data. And fortunately, the question's simply asking me for a hydrocarbon. That really simplifies the process quite a bit when we don't have to ferret out the answer to the grams of oxygen present. So we have a hydrocarbon. A hydrocarbon simply has hydrogen and carbon present. And we're going to combust it, and we assume that we're making complete combustion. So we make CO2 and water for this. And the question tells me I have 7.2 liters of CO2 at STP and 7.2 grams of water. Now, typically we say on these you want to get to mass, and then we want to go from mass to moles, and then we divide by the smallest and multiply till whole. Now, here we get to actually bypass the mass. You can go ahead and go to mass if you want. It's going to add an extra step. You could solve PVNert for mass and then convert mass to moles, but hopefully you will recognize that if I have 7.2 liters of carbon dioxide, I can get to moles of CO2 pretty quickly by using the molar volume, 1 mole of CO2. Now we're talking about CO2 right now, not carbon, that we ultimately need is 22.4 liters. And that will then give us 0.321 moles of our CO2, but we need moles of our elements here. So this is a little twist, and you can follow those steps that I give you, but it's nice to be able to do it a little faster. Now, if I know moles of a substance, I can go to moles within by using our subscripts. So I have that many moles of CO2. I want to get rid of moles of CO2 and go to moles of carbon. And that's a 1-to-1 mole ratio because of that implied 1 in the subscript. Now let's deal with the water. I have 7.2 grams of water. And when I do these, I like to use my mass to mass within ratio. We don't have to in this case because I don't really need mass of my elements. I'm really after moles of my elements. So I'm going to get to moles of water, and mass to moles, use molar mass. And now I can go moles within because there's 2 moles of hydrogen for every 1 mole of H2O. So that's a little bit more of a standard approach to these. Using that mass to mass ratio is really what you would have wanted to do had there been oxygen present in this compound. And we are able to move a little bit more swiftly to moles here. So I have 0.799 moles of hydrogen. Again, you can do that mass to mass ratio and just take you a couple of extra steps. So I have moles of each. So we've got to find our way to get to the moles. Now we want to divide by the smallest, and the smallest is the carbon, so we're going to divide them both by this number. And I get a 1 to 2.49 ratio. Now we can't have a half there. We do need to multiply that by a factor to get a whole number. So I would have 5 hydrogens, and if I do it to the hydrogen, I have to do the same multiplication to my carbon. And so I'm also going to multiply carbon by 2, and that gives me 2. So that means my empirical formula is C2H5. So that's what we'll be bringing through into the next parts of our question. Now the next one is a more traditional stoichiometry. We want to know how much oxygen was required. So if we're going to do a traditional stoichiometry, we have to balance. So we'd have C2H5 plus O2, and this would give us H2O plus CO2. All right, and we want to look at the combustion of the hydrocarbon back in that previous sample. So let's take a look at our balancing factors here. I need a 2 here because I have 2 carbons. But look, I've got 5 hydrogens. So I've got an even odd issue, which means you have to backtrack and you have to multiply by 2 there to get this to be an even number, because multiplying by 2 always gets an even number. So let's try again. Now I have 4 CO2s and I have 10 hydrogens, so I would need a 5 here, and that then gives me 8 plus 5, which is equal to 13 oxygens. And again, I'm left with yet another even odd issue here, which means that you have to multiply all of those subscripts by 2. And so that would be a 10, and that would be an 8. And then I would want to recalculate my oxygens, but I likely need a 13 right in front of those oxygens. Now I have 10 plus 16 is 26 oxygen, so I can put a 13 here. And I finally have a balanced equation. Very tricky. When you have that even odd problem, you have to go back and remultiply all the subscripts by 2. So now I had 7.2 grams of water, and I want to know how many grams of oxygen is required. So I need to go mass to moles, then moles to moles, then moles to mass. So now it's a pretty traditional stoichiometry. You guys all rocked at stoichiometry, so I really think that you're going to do a good job here. I'm going to go ahead and make myself a little railroad track to simplify and get rid of grams. There's 18.02 grams. Whoops, 2 grams of water. Let's try again. 18.02 grams of my water per 1 mole. My stoichiometry tells me that it's 10 moles of water for every 13 moles of O2. And now I'm talking about diatomic oxygen, so I have to use that 32 grams of O2 for every 1 mole of oxygen. And the answer to that part is 17 grams of oxygen. So I think the trickiest part here was actually balancing this. And the rest is your traditional stoichiometry, where you're trying to cancel out units. Grams of water, moles of water, should have labeled that one, moles of oxygen, and I do end up with my grams of oxygen. Now, let's go on to the next part. Now, we've seen this before. Again, that seemed random in the tools of the trade, but this is now our payoff. Now we want to know what is the molar mass, because if we have an empirical formula and we have a molar mass, we can get to the molecular formula. So that's what it's building to. When you see freezing point depression, boiling point elevation, you want to write down the 2 formulas right away. Don't get sloppy about this. I've had some students ask me questions, and really all they had to do was write this down, and they had their own direction. They did not need me anymore. Now, if I'm not asked for molality or given molality, I like to write molality out in its fullest in this context. If you're asked for molality or given molality, you don't have to go through this step. So it's mass over molar mass divided by kilograms. Remember, it's of the solvent. KF. Now, it would be times I. I like to just keep all of mine together. And notice that we would assign a 1 to I when it's covalent. And we have a hydrocarbon. Hydrocarbons are covalent. Now we plug in all our information that's given. We were told this value. The only ones you have to memorize are waters for the pure substance, the melting and freezing. And this is minus 63.5. My hydrocarbons, my solutes, this is 0.600. I want kilograms. That's grams. I need kilograms. Make sure you go the right direction. I've had quite a few people go the wrong direction on this. Tells me my constant. Funny units, but we just need to keep everything in molal and Celsius and we'll be fine. And so this is 4.68. Now, I have one unknown in this equation. That's what I'm going to start with. And if I solve that equation for delta TF, I find out that delta TF is 0.500. So I can take that number and bring it down here. So solved this for delta TF, plugged my answer in here. My only unknown is that molar mass that the question asked me for. And again, you won't see everybody using molar mass, but I like it to distinguish it from molality. So 56.16. Do not forget units. Sometimes they're counted on AP, sometimes they're not, but it's simply the best habit to get into. So now we're going to use that information in our next part, D. And again, if you didn't get that part, you can assume. And let me show you how you want to assume a reasonable number here. Remember that our number of empirical formula units that would make up our molecule is the molar mass of our molecule divided by the molar mass of our empirical formula. Now, hopefully you got your empirical formula above. You get some of these steps at least. And the molar mass of our empirical formula would be 29.07. It was C2O5. So that was 29.07. Now, this has to be a whole number. So if you have to make an assumption, make it 2 times this or 3 times this or 4 times this, but something reasonable. Now, we actually had from our previous problem that this was 56.16. If we did that division, we'd get very, very close to 2, certainly within any experimental error. So that means there are 2 of those empirical formula units in our overall molecule. So you take that whole number that you get, and we're going to multiply each coefficient by that number. So our answer would be C4H10, likely butane. So that's the last video. Let's have at some homework and get this information under our belts. See you in class.